thank you very much. Okay, so this is joint work with Benoit Collins, Lee Liu, and Vern Paulson, and Lee is here at the conference. So many of you have heard of William Slofstra's breakthrough result that there exist non-local games or correlations where the optimal behavior can only arise in the limit of infinite entanglement. So as you get more and more entanglement, the performance is converging towards some value. So this suggests that maybe there's something interesting going on with infinite entanglement, and it's worth exploring this world. What happens in with infinite entanglement? What's the theory of information processing when this resource is available? And so what is infinite entanglement? Well, there are different ways that one can approach the concept. So one notion is to have states in the tensor product of two Hilbert spaces, and I've written here, a Schmidt decomposition. And the sums of the squares of the Schmidt coefficients, of course, they have to add up to 1. It's a normalized state. But the sums of the Schmidt coefficients squared multiplied by their logarithm squared can diverge. It's possible to come up with sequences like this. So the entanglement entropy can be infinite of such a state. And it turns out that whenever a state is in the tensor product of two Hilbert spaces, they don't have to be separable. The two Hilbert spaces, HA and HB, they can be each of uncountably infinite dimension. And nevertheless, any state in their tensor product will have a Schmidt decomposition of this form where there are a countably infinite number of Schmidt coefficients. So let's call this notion of entanglement the tensor model, where we're in the tensor product of two Hilbert spaces. Okay, so there's the tensor model. So let's consider the state like this. So if we're in a world with infinite entanglement, we can imagine that Alice has an infinite sequence of qubits. It's going off to infinity, and so does Bob. I shouldn't have done that. Okay. I pushed that, okay. Sorry. And that their corresponding qubits are entangled. So, but what is a state like this? What are the Schmidt coefficients? And if you stare at this, it doesn't make sense. It doesn't sort of reduce to something of this form because they would all multiply out to 0. So this is a form of entanglement that doesn't seem to be in the tensor model, but it's something that conceptually we can think about, and it's actually possible to capture this in a model called the commuting operator model, which many of you are familiar with, and I'll say more about this model later. So let's call this the commuting operator model. So this is just one state in that model. It's not. There are many other states that don't look at all like this. This is just one example. And then here's a third approach of dealing with entanglement, which is infinite entanglement, which is sort of to sidestep the question and just consider very large finite entanglement and what happens in the limit. So by this I mean we have you can consider infinite sequences of states that are finite dimensional or at least in the tensor product model, and look at what happens with regards to the performance of some information processing task. Maybe it approaches some limit as you go down the sequence. But the sequence itself need not converge. So here's a sequence where the kth term in the sequence has the first k of Alice and Bob's qubits in a Bell state, and the rest of the qubits are unentangled. This is in each of these states is in the tensor product form, but this is not a Cauchy sequence, so it doesn't make sense to talk about the limit. They don't get close to each other as you go down the sequence. So the sequence of states need not converge, but what you can do with them might be converging in some sense. And let's look at this. It turns out this sequence is not all that useful, but another sequence of states, these so-called harmonic states, it'll come up when I talk about embezzlement later on. So here the Schmidt coefficients are the square roots of the, the first d terms in the harmonic sequence. And what happens to these states when d approaches infinity? Do they converge? Well, they actually converge to a vector, but to the zero vector. So it doesn't make sense to think of the limit of this as a quantum state either. But maybe there's some capability that's converging as you go down the sequence. So just for the purposes of this talk, let's call this the sequences model. That's not standard terminology or anything. So we have these, three notions that we can associate with infinite entanglement. And the subject of the talk is not non-local games or non-local correlations, but let's just, I just want to briefly comment on that topic. So in the context of non-local games or non-local correlations, let me define the commuting operator model. Remember, I referred to it, but I didn't say anything about what it is. And there we have, Alice, we have some kind of a non-local game where Alice gets a question and Bob gets the question, and they're both required to produce answers, and they can't communicate with each other. I think this has been discussed in many of the talks here. And there's some thing that we refer to as a compound register, the joint state of both registers. And that has a Hilbert space associated with it. So there's a global Hilbert space, but there are no local Hilbert spaces for Alice's data or Bob's data. But what we have is all the measurement operators that Alice can use, they commute with all the possible measurement operators that Bob can use. So we can take some kind of algebraic closure of these operators, and they will commute with each other. Okay. And now if there's a tensor product structure, this will happen because everything in Alice's measurements will be of the form A tensor I, and Bob's will be of the form I tensor B, and those commute. But even without having that form, we can have this commuting property. And in terms of non-local correlations attainable, let me just review some stuff that's known. So remember, there's the tensor model, and then there's the sequences model, and the commuting operator model. So this is the first one I discussed, and then the commuting operator, and then sequences. And so Slofta showed that the first two are not equivalent to each other. Actually, his first paper showed that the tensor is distinct from the commuting, but a later paper in 2017 showed that these are different. So there are things that you can accomplish, by ever larger and larger sequences of entangled states that go beyond what you can accomplish with just an entangled state in the tensor model. And it's still an open question, a big open question, whether the sequences model, what you can do in the limit of tensor entanglement, approaches the commuting model. And this question is equivalent to a major question in the theory of operator algebras, which is called the Kahn embedding conjecture. If the Kahn embedding conjecture is true, if and only if you do not have a proper containment. And if you do have a proper containment, Kahn embedding is false. Okay, but this talk is not about non-local games. It's about another task that's called embezzlement. And this was originated by Van Dam and Hayden. And so to describe this, imagine that there's some state that phi AB that Alice and Bob would like to create, and they're physically separated from each other. And it's some finite dimensional state. It could be, for example, a Bell state. And now they can't do that with local operations out of nothing, but we give them a resource. They have this catalyst state, psi AB, which they start with, and they're able to use that to help them construct a state. Phi is the catalyst, and they can use that to help them construct phi. But they want to do it catalytically, so that at the end of the process, they haven't they still have this state. So they're creating additional entanglements. So this could be their initial state. And with local operations, so for the moment, let's just assume epsilon is 0, and they're doing this perfectly. They're creating additional entanglement by local operations. And it's known that you can't do that because local unitaries preserve the Schmidt coefficients, so the entanglement entropy can't increase. And if this is an entangled state, this would have higher entanglement entropy. But what's remarkable is that you can approximate this. For any epsilon, you can come up with a catalyst state and local operations that approximates this with fidelity 1 minus epsilon, so arbitrarily close to 1. So I think that the terminology embezzlement is kind of tongue-in-cheek, and well, I guess the idea is that you're stealing some entanglement from this state and putting it over here, but you're stealing it in a way that's very difficult to detect. So you're unlikely to get caught if you return the state to the bank. And they conduct an audit. And it's also shown in the same paper that the catalyst, the entanglement of the catalyst must approach infinity as the precision parameter approaches 0. Okay, now this is not a non-local game result in the sense that, well, at first glance you might imagine, you know, if there's some claimed implementation of this, you could have two distinct space-like separated, you know, Alice and Bob, and you could give them as input the catalyst state and require that they send back a copy of of that same catalyst state or something close to the catalyst state plus the additional entangled state. But that test doesn't really work because Alice and Bob might have a prior entangled state that they got together and created before the game started, and they could just be sending you back the catalyst state without doing anything with it and just giving you back that prior entangled state. So it's not really amenable to analysis like non-local games where you can, you know, prove something about the entanglement that they used if they can get some performance in a non-local game. But in spite of that, there have been some constructions that are based on the idea of embezzlement that have led to non-local games. And first with classical inputs and outputs, and then, with quantum inputs and outputs, so sort of a generalized non-local game. But the most recent results by Zhenfeng Ji, Debbie Liang, and Thomas Vidic showed that, you know, based on the idea of embezzlement, you can come up with a non-local game such that the success probability approaches 1, but only in the limit as the entanglement approaches infinity. So this is implies Lofstra's prior result, but it's actually quantitatively stronger, the relationship between the how the entanglement approaches infinity as the success probability approaches 1. Okay. So it's, well, that's, I'm asking the question, what happens with embezzlement if we actually let the catalyst be infinite, an infinite entangled state? So nothing written on the slide rules out the possibility of perfect embezzlement, but it turns out that, so if we want to embezzle, let's say, a Bell state, it turns out in the tensor model, even with infinite entanglement entropy, you can't achieve fidelity 1. So in the sequences model, you can approach fidelity 1, and that's just a restatement of Van Dam and Hayden's result. And in the commuting model, you can achieve actually fidelity 1, and there's a sort of a nice, or at least a cute, intuitive picture along the lines of the Hilbert Hotel. So imagine this state where on the right side we have this infinite tensor product of Bell states. So each of these boxes contains 2 qubits, and let's say the first qubit is in Alice's lab and the second qubit is in Bob's lab. And on one side we have an infinite tensor product of Bell states, and on the other side just an infinite tensor product of product states. And the purple state in the middle, let's call that the target state, and the rest we'll call it the catalyst. And well, if Alice and Bob just move all their qubits to the left, they just do a left shift, then that state would become the state where the purple state, the target state, changes from ket 0, 0 to the Bell state, and the state of the catalyst hasn't changed. Okay, so this is a kind of a cartoon, and that's schematically, well, I'll be drawing pictures like this later. Think of each dot as representing a qubit, and when there's a line between them, they're in the Bell state, and when there isn't, they're just in the basis state, they're in a product state. So we just do this left shift. So it turns out that there is a commuting operator framework that can be defined where this can be formalized. The way I've described it, it might sound like a sort of hand-wavy, just cartoon that can't be made formal, because it certainly can't be made formal if our model is the tensor product of two Hilbert spaces. Okay, but this talk is not about embezzlement. It's about something. It's in a way stronger. It's self-embezzlement. So for embezzlement, we imagine the state you want to create is some state, fixed state, like say a Bell state, and then the catalyst is some very high dimensional state, because if the precision parameter is epsilon is very small, we need a lot of entanglement to do the embezzlement. Self-embezzlement, they're trying to create, the target state is the catalyst state. So they can start with a lot of entanglement, but that makes their job harder in terms of what they have to embezzle. Now, if we just say, does there exist any state for which you can do this? Well, you can do this if you're allowed to set the catalyst to a product state, because then there's no entanglement, and it's kind of trivial, but then it's just, you're doubling the entanglement, but 2 times 0 is still 0, so it's kind of vacuous. So we add a non-triviality condition, which is that we require the state to be CHSH violating. Okay, so there's a parameter here, and when the parameter is set to root 2, we're saying the state enables you to get the maximum violation of CHSH. And when the parameter is 1, it's no violation, and they're in between origins. And so now let me define this approximate self-embezzlement. So for such a scheme, we have a catalyst state, psi AB, and we require that it be, if we want to get an epsilon approximate scheme, that it be CHSH violating within epsilon. So almost CHSH violating, and that the local operations do the embezzlement almost, like within fidelity 1 minus epsilon. Okay, and the perfect case is when epsilon is equal to 0. So is this possible? So it sounds too good to be true, right? But maybe the original description of what embezzling is a little bit counterintuitive also, so we have to be a little careful. We really need to prove things. So our results are, first we show that in the sequences model, so which includes subsumes the tensor product model, the tensor model, you can't get arbitrarily good self-embezzlement. The epsilon can't be less than 1 over 50. You can't get closer to 1 than that. But in the commuting model, you can get perfect self-embezzlement. You can achieve it. So now we have a constant gap between the two models, between what the sequences model can do and what the commuting operator model can do. But it's not for a non-local game. So no con embedding is not resolved as a result of this. And although there were the ordinary embezzlement protocol had the property that it could somehow be massaged into a non-local game, we don't know how to do it for this. And perhaps at the end I might comment that it's not going to be easy, because there's some evidence that you can't do this in a black box sense. It's not only do we not know how to get a non-local game separation out of this, but if we're using the self-embezzlement in some kind of black box fashion, then it's provably not possible. But maybe there's some other creative way of thinking about it. But we don't claim anything about non-local games here. And let me mention that Navasquez, sorry I misspelled the name, and Perez Garcia, they showed a constant gap separation for another task, which is steering. And that also doesn't lead to a non-local game, at least it's not known to. Okay. So, oh yeah, so that second theorem is that commuting model is actually based on a perfect protocol in a model that we call the C-star circuit model, which I claim is sort of a natural way for reasoning about these infinite dimensional systems that we're working with. And you see, it's not a non-local game. In the case of a non-local game, you just have this entangled state and not much happens. I mean, Alice does a measurement and Bob, and that's all that's going on. But for embezzlement, we have these registers. We have 4 registers in play, the 2 that are entangled and the 2 that are not, and then at the end they're both entangled. So we need to be able to define localized reversible dynamics. So think of these as the local unitaries. So we need some notion of the register, we need a kind of a more fleshed out language to talk about the individual registers and to be able to say that the state of this register and this register combined is the same state at the end, even though the global state has changed, and that this state, these 2 registers, is the same as this. And we sort of achieve that through the C-star circuit model, and then we can transform that into a commuting model if we prefer that. Okay. So I guess I have a sketch here of the first theorem, the no-go result for the tensor model, but because of time, there isn't time, I'm going to just skip over that. It's the slides will be made available, but and the details are in the archive version of this, so I'll just refer you to that. And I prefer to use the time left to talk about the commuting operator model and the C-star model. And at a sort of schematic level, I guess it's very simple. You can probably already guessed how the self-embezzlement works. You know, Alice has the pink ones and Bob has the baby blue registers, and these are all qubits. And these are, this pair is entangled and this pair is unentangled. But if they just, move around the qubits, then, just rearrange them, then Alice can, and Bob can locally just move, every second entangled state here up here, and then just sort of scrunch them so that they're all beside each other. And then these unentangled states have to have somewhere to go, so we make the whole left side unentangled. So, and in fact, there's a paper, Infinitely Entangled States by Kale et al., where they actually allude to this, but it's just a passing remark. They talk about a state like this and say that it's unitarily isomorphic to 2 copies of itself. And that's true, but in order to be interesting, you have to have some notion of locality, because every state is unitarily isomorphic to any other state if it's in the same Hilbert space. So I think they really mean in the sense of local operations. And in the sense what we're doing is helping to formalize this. So the C-star circuit model, we can think of states as maybe vectors in Hilbert spaces, but we never get to see that, right? What we get to see, we can perform a measurement and we get to see the outcome of the measurement. And what's actually causing that is just something that we can imagine. It's some infrastructure that allows us to compute these outcome probabilities. And an abstract state is it's an abstraction of this. It actually goes back to von Neumann, this way of looking at things, is to just have a function that directly maps the POVM elements to probabilities. And so then the picture looks like this. It's just, we don't really care exactly how S, S is just some function that, maps all the possible positive elements to probabilities, or if they sum to 1. And now there's a bit of a problem here, because where do these operators these measurement operators live? I mean, up here they lived in the same Hilbert space, but we've removed the Hilbert space, so they've lost their home. And the answer is they're elements of a C-star algebra. And the C-star algebra is it's an abstraction of operators on a Hilbert space, but without actually having the Hilbert space. We just have this abstract operation, the star, which plays the role of a dagger in a norm. And it's complete with respect to the norm. And an abstract state acts on the C-star algebra. So the bounded operators on a Hilbert space would be an example of a C-star algebra. But a more interesting example, and maybe I'm glad at least I have enough time just to describe this, because our work is based on this car algebra. This is a particular C-star algebra that's where there's no Hilbert space explicitly given. Imagine we have a countably infinite number of qubits, and the algebra is going to be infinite tensor products of polys, but of finite weight, where all but finitely many of them are the identity. And we can take finite linear combinations of these. You know, I mean, think of these as sort of formal symbols, because I'm not asking you to we're not really defining what it means to do this, because this would be some kind of infinite matrix. But we can take linear combinations of two of them, because we can always factor out the infinite tail of identities, and we're just left with a finite portion. And this generates a star algebra, which is like a C-star algebra but without the norm. And then we can define a norm, because every element in this star algebra is some linear operator tensored with infinite number of identities. And then we can just define the norm to be that norm of M and take the completion with respect to that, and we get a C-star algebra. And I'll just say, I mean, the clock is running out on me, that it's fairly easy to define this infinite tensor product of Bell states as an abstract state on this C-star algebra, because if you want to define it on the generators are only interacting with the, the first two generators are acting on the first two qubits and the second on these two. So we just have separate terms when we evaluate this, and we take the product. Now, if we didn't have this condition that if we allowed infinite weight, then we could get into trouble at this point, because we may have an infinite product, that's, let's say, all minus ones. And then it's not clear, is that plus one or minus one at the end? But we don't have such problems, because there are only finitely many terms that are not one in the sum. Okay, now for multiple registers, we take the tensor products of the C-star algebras. So let me just try to make a quick beeline for the end here. So there's a way of doing that. There are some subtleties that I'm just going to gloss over. And when we have joint states, it makes sense to talk about product states, to define product states and partial traces. So we can talk about the individual registers. And I guess one other point that I'll make before I skip to the end is we can define the reversible dynamics as the star automorphisms of the algebra to itself, which is kind of the analog of unitary operations. They're just coordinate system changes. But the star automorphisms, and they kind of change the observables. So it's like a Heisenberg picture here. The modified state, you change the observable, in a sense, not the state. And then we can talk about circuits in this model. So I'll just skip over this and say that there are some star automorphisms or inner automorphisms, which are just unitary elements of the C-star algebra, and conjugating by that gives you a star automorphism. But another example is like for this car algebra is the left shift. So now think of doubly infinite, and it doesn't really matter the distinction, tensor products, and just shifting all the qubits to the left, which is equivalent to shifting the generators to the right. That's a star automorphism, but it's not an inner automorphism. And now basically we have all the infrastructure to make sense out of this and make this picture into a reality. And based on this, we can define a commuting operator model. I won't go through this. Maybe I'll leave the slide up at the end. And then using the GNS representation theorem and then some star cross product, we can convert outer automorphisms to inner automorphisms, and then apply GNS to convert from the C-star model to the commuting operator model. Sorry, that was a little bit fast. So that's the end. And maybe I'll just leave this slide. I don't know if there's any time for questions, but that's the definition of the commuting operator model. Thank you.
Thanks, Richard, for the great talk and for keeping time. So are there any questions for Richard?
Hi, this is kind of a naive question over here. So you were using fidelity to define, I guess, success in an approximate sense. So I guess in an infinite dimensional Hilbert space, I guess some of the different measures of success which are comparable in finite dimensions can be quite different if the Hilbert space dimension is large. So can you comment on, is fidelity, why do you pick fidelity? Is that the right?
Well, in this context, the fidelity works. So I'd like to maybe hear, maybe offline if you have time, about these other contexts where there's a problem.
Yeah.
But if I understand your question, you're saying there are contexts where fidelity maybe doesn't work, or?
Well, say compared to like trace distance or something, I don't know.
We could translate it into trace distance.
Mm-hmm.
The trace distance would approach 0 instead of the fidelity. Well, actually, sorry, in this model, there's a no-go result, and it would apply in both definitions. That in the tensor model, you can't do it if we use trace distance to measure distance. Mm-hmm. And then in this exotic C-star model, well, we don't have any epsilon, we don't have any error, we just do it perfectly.
Yeah,
So,
sure.
but maybe you have more to ask, but we could take it offline.
Yeah.
Okay, so so you switched to the C-star algebra model to model infinite systems with commuting operators.
Sorry, where are you? Okay, thanks.
Yeah, and so that's a step that I certainly endorse. But then there's a step that you didn't take, which is that you can further dress up your algebra beyond making it C-star. You can make it a von Neumann algebra, which you can even define abstractly as a C-star algebra with a predual, and then you only take states from the predual in that formalism. And then that also fixes one thing that you mentioned on one of the slides, which is that there's one favorite tensor product for von Neumann algebras, so you don't have this min and max problem that you have for C-star algebras. So my question is, does your work with von Neumann algebras, or is that to be explored, or? Okay,
so there is this model really makes sense for any C-star algebra, and you can choose which tensor product you want to use. So in a way, there's a family of different models. We're only using the Carr algebra, the simple one, and in that case, the min and max tensor product coincide.
Right.
Because it's hyperfinite. And that's the simple one, and it works. Now, I think you can take some kind of, maybe correct me if I'm wrong, we have some experts here, but you can always enrich the C-star algebra by taking the von Neumann algebraic closure of it, but we don't need it. So a von Neumann algebra is a C-star algebra with additional properties. I don't know if I'm addressing your question.
Yes. There is a von Neumann algebra envelope for every C-star algebra, but that one is kind of larger than necessary for constructions. But maybe that is a kind of answer to the question. My real question was there a reason, I guess, beyond that's all you needed, that you decided that you liked C-star algebras rather than von Neumann algebras?
Well, we want to use the simplest model. Like in a way, if we could do it with on the tensor product model, if there was a positive result, then in a way, we don't need more resources, more exotic resources, so we don't use them.
Oh, okay.
Okay, so maybe for the sake of keeping time, we're gonna postpone other questions to offline and move on to the next talk. But first, let's thank Richard again.